The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, one of the really important things in this course on spectroscopy is being able to write effective Hamiltonians to describe the problem that you're going to be solving. And so at the beginning, I'm doing an exercise in two versions of effective Hamiltonians before starting to pick up the material of spectroscopy in a logical order. And so it's a taste of what's to come. It's an example of the kind of problems I hope you'll be able to solve and like solving. And I said there was a problem last time. The problem is described at the top of the first page. Now, probably the best thing would be for you to submit that answer to me on Thursday. Or to one of the members of my group, if you're, but I'm mostly going to look at this just to say, oh yeah, you did it. And my idea is that you're going to do these problems just to sort of refresh your memory of perturbation theory and get a little bit insane with the awful algebra that ensues. Okay, so the problem that I wanted you to do is a diatomic molecule, and it's a vibrating rotor. And so we have a potential, and the potential is got the harmonic term. I just want to make sure. And then a cubic term and a quartic term. So these are the operators that you're going to be dealing with using perturbation theory. And we also have the rotational operator, which is the moment of inertia operator, and that's h bar squared over hc. That's just because of the units we're using. And it's 1 over 2 mu r squared. And I'm going to convert r into q in a moment. But this is just analogous to the kinetic energy operator, 1 over 2 m p squared over 2m. And we get a j squared here. Okay, so we write b of r by saying r minus re is q. We write b of r and we do a power series expansion, and we get be 1 minus 2 q over re plus 3 q over re squared. So the problem we're going to solve, that you're going to solve, involves q squared, q cubed, q fourth, and q to the 1, q squared. And we're going to put that all together in a way that gives you something that's related to the energy levels of a diatomic molecule. So the energy levels for a diatomic molecule, they have two quantum numbers, v and j. Actually, you'll see that they have omega and lambda and s and sigma and other things later. But for an ordinary molecule without any angular momentum, any electronic angular momentum, we write the energy levels in a naive way. got this wrong yesterday. And then we have plus j plus 1 times BE times, BE minus alpha E, B plus a half, plus gamma E, B plus a half squared. And that continues. And then we have minus j squared, j plus 1 squared, d E plus beta E, B plus a half. So you see what we have is a bunch of expansions in powers of E plus a half and jj plus 1. And so in order to describe the energy levels of a molecule, or the problem that I've asked you to solve, you want to get omega E, omega xe, BE, alpha E, and DE from the quantities K, A, B, and mu. So we have the harmonic, the cubic, the quartic, and the mass, and that will enable you to derive values for the things that you'd actually observe in the spectrum. You could carry this further and get a YE and gamma E, but I'm not too cruel. And so that's the problem. And okay, so let me go to the other board. So what do we do? How do we use perturbation theory? Now this is really a lengthy review of what we did last time, but it's still better to see it. We expanded the Hamiltonian into a zero-order part and a perturbation part. We expanded the energy into a zero-order part, which is eigenvalues of H0, and first order and second order, etc. And so we got a zero-order equation and this is what we use to describe, to define our wave functions. Our wave functions are eigenfunctions of the zero-order Hamiltonian. The energy levels are the eigenvalues. And there are many choices of H0. It's usually not necessary to make your choice of H0 read the mind of the molecule. It's just, usually you choose H0 because it gives you things that you can do without breaking a sweat as far as writing down values of matrix elements. Once you've written down values of matrix elements, the computer does all the work. And it's nice to be able to have a way of writing the matrix elements which really don't even require you to write them. You say, Mr. Computer, you write them, because they are gotten by this simple formula. So, but you don't have to do that. This H0 is whatever you like, but it provides the words you use and the images you use to describe what you're seeing in the experiment. And sometimes that's valuable. It also provides you with a starting point. When you start out in interpreting an experiment, you have energy levels. And they don't come with any hints on them about, well, they usually don't come with many hints on them what they mean. And your job is to somehow recognize the patterns in the real spectrum and relate those patterns to the truth. And that's a non-trivial matter. And so if you have a good H0, one that does mimic what the way the molecule thinks, you will have a much easier job of making sense of the experiment than if you have a bad one. But that's counterbalanced by wanting to have the computer essentially do all the work. So you have to make a compromise. Okay, so we choose this that defines basis states. The H0 for a diatomic molecule is a harmonic oscillator plus a rigid rotor. And so H0 is, I can never remember where with these. So that's the zero-order Hamiltonian. Rigid rotor, because it's a constant, and a harmonic oscillator. And so the zero-order energy levels are omega EV plus a half plus EE JJ plus 1. Well, gives you E V0 J is equal to that. And you get eigenfunctions, which are V and J, MJ. And those are the things that you manipulate. But one of the things about matrix mechanics, which is making it really beautiful, is that you never unpack these things. You never ask, well, what are these functions? These are labels of states in some abstract space, and they have certain properties that you can write down their matrix elements without thinking about them. And you almost never look at what the functions are. In fact, this is actually not a function. To make this a function, you have to write this quantity here. But it is wonderful. One of the wonderful things about matrix mechanics is you're dealing with vectors, and you're not looking at the differential operators, and you get to do things that are terribly profound without doing very much work. Okay, so we have H0. Now we have the perturbation term. And since we're dealing with anharmonic oscillators, we'd like to be able to say something universal about the coordinate, displacement, and the momentum, which is conjugate. And so it's a wonderful thing to replace a coordinate that depends on all sorts of things, like what system of masses you're using and what coordinates you're using, to replace them by a dimensionless quantity. So we have this scale factor, 2 pi c mu omega e square root. This is a dimensionless quantity. And so that makes it universal. And so if you know how to strip out the molecule-specific things, the reduced mass and the force constants, I guess. No, it's there. OK. If you strip out the molecule-specific stuff, then you're going to be dealing with universal things, and you solve problems once, and then you just know how to scale them. OK, and the same is true for P. The factor here is, you see, I have to look at my notes because I don't know what the factor is, but I only have to do it once. 2 pi c mu omega e square root p hat. And then there's a further reduction, Q. Now, if I tell you what are in the basis set of the harmonic oscillator, where we have these kinds of functions, V, what is the selection rule for matrix elements of Q? Most of you know that. Most of you know that from the Schrodinger picture, from a first course in quantum mechanics. You know that the coordinate changes the quantum number by plus or minus 1. OK, and so the matrix elements of Q are going to be delta V of plus and minus 1. And many of you also probably know what the actual value is, but you don't really, you know, but you don't know how to dig it out, because it's entangled with all this garbage and factor a square root of 2. And so it doesn't look memorable. So if we replace this by 1 over square root of 2 times A plus A dagger, then we now have simplified Q in terms of operators which have two wonderfully convenient properties. A decreases the number of quanta of the thing on its right by 1. A dagger increases the number of quanta of the thing on its right. And it gives you a number. They both give you a number. And so if you write it this way, A v plus 1 v, you get v plus 1 square root. And if you write v a dagger v minus 1, you get v square root. So there's only one non-zero matrix element of A and A dagger. Q has two non-zero matrix elements because it's a sum of A and A dagger. This is simpler, and this is wonderful because suppose I tell you that I have some operator that's Q1, Q2, Q3 squared. And I ask you, well, what's the matrix element between this number of vibrational, this combination of vibrational quantum numbers and that? And as soon as I tell you that, you know exactly how many A's and A daggers to pull out. And then you know exactly how to evaluate all the matrix elements. So this simple thing is saying whether it's A or A dagger, it doesn't matter. You just take the larger of the two quantum numbers and take the square root. That's all you ever have to remember for harmonic oscillator matrix elements. The larger of the two, and you also recognize is like a plus, and so it's increasing, and no dagger is missing the plus, and that's decreasing. And that's all there is. And so you can remember then all the matrix elements of Q and P and any integer power of Q and P. And if you're clever, any non-integer power of Q and P. That's later. OK, so.
Well, the Q hat is 1 over root 2, right? Not.
Absolutely.
It's wrong on the lecture notes, too.
It's wrong on the lecture notes. Yeah. Holy mackerel.
What's the minus sign in one frame?
Well, it's a factor of 2 in this case. Yeah. OK, well, sorry about that. I don't know what I say. I don't know what I write. I don't know what's in my notes. I mean, and 2 out of 3 is not good enough.
Well, you said the right thing.
Oh, OK. Well, OK. Well, that's good. All right, so. Now, there are some other things. And last time when I went through the beginning of this, I decided not to introduce these other simplifying factors. But it turns out you really want them. So we have a couple of other ways in which you deal with strings of A's and A daggers. And one is the number operator, which is A dagger A. We want something which will return the number of quanta. So if we write n on V, we want V, V. And see, A lowers V, A dagger raises it. So if we have an equal number of A's and A daggers, the matrix element in question is diagonal in V. So, but now you look at this and you say, well, I'm going to apply this to the V state, and I'm going to decrease V by 1. But the larger of the two quantum numbers is where you started, so that's square root of V. And then I'm going to increase it again back to V. And so we get a factor of square root of V from both of these. And that's why we get this. So that's the number operator. And that's convenient. And then we have some commutation rules. And so that's just A dagger A minus A dagger. And so you can figure out what that is by applying this to V. But I'm just going to tell you it's minus 1. And if you do it in the other order, A dagger, it's plus 1. And then there's commutation rules involving N and A dagger. This is quantum mechanics, so you have to watch out the order in which things appear. And one of the beautiful things when you have n with a daggers, you just get a dagger back. When you have n with a, you just get a back, but it's a minus sign. So these little tricks enable you to make tremendous simplifications. And so now let's look at q squared. Well, q squared is 1/2 a plus a dagger squared. And so we immediately know we got a squared, a dagger squared, and then we get a dagger plus a dagger a. So that's the number operator. And this is the number operator written in the wrong order. And so you can permute these. So suppose you have a dagger. You can write that as a dagger plus a dagger a minus a dagger a. And then you combine these two terms. And those two terms are the commutator a dagger. And the commutator a dagger is 1. So we take these two terms, combine them, they're just 1. And this is the number operator. And so to take a term which is written not in the order of the number operator and reduce it to the number operator, you ask, how many times do I have to permute an a dagger past a? And so each time you have a term like a dagger or a dagger a, you're going to get a number operator, but you're going to get something extra from this one because you had to permute. Okay, and so it turns out you can very quickly look at these sorts of things and write down what they are in terms of the most compact form. And so we get 1/2 a squared, a dagger squared, plus 2n plus 1. So this is the number operator. It's not a constant. If you multiply it on v plus 1, you get v plus 1, not v. Okay, so this is how you reduce a q squared. You can reduce p squared similarly. I'm not going to do it. It's in the notes. When you do q squared plus p squared, you discover from the definition of p, which I didn't write down today, which has a minus, we have a dagger minus a, but there's an I in front. You end up having these raising and lowering operators squared cancel, giving you 2n plus 1 times 1/2 from each, and the overall matrix element of H0 comes out to be just n plus 1/2. You have 2n plus 1 times 1/2 omega e is what you get by adding the 1/2 p squared plus 1/2 q squared stuff. So that you discover that q squared is not diagonal, p squared is not diagonal, but their sum is. And that's good. You want it to be diagonal because you wanted those to be eigenfunctions of, you wanted to have harmonic oscillator eigenfunctions. Okay, so now the next blackboard, I'll do over here. Suppose we want q to the third power. Well, we know, we want the hat. We know that we're going to have 1 over square root of 2 3 times, so it's 2 to the minus 3/2. And we know we're going to have a dagger cubed, and we know we're going to have a cubed. And then we know we're going to have 3 terms that have a dagger, a in the various orders. And we're going to have 3 terms involving a dagger. And so the trick before one gets into heavy-duty perturbation theory is to simplify these things. And so because there's 3 terms, we know we're going to get 3 times some simple thing, a number operate, well, first of all, A dagger, we've got 2 A daggers and 1 A. So the overall thing is going to increase V by 1. So it's going to look something like N A dagger. So let's extract from these 3 terms 3 times A dagger N. And so what does that look like? A dagger N looks like that. So that's one of the 3 terms. We have A dagger, A dagger, and we have A dagger, A dagger. Okay, so this is right. This one, we have to permute the A past the A dagger. So we have to do 1 permutation. This one, we have to do 1 permutation, then 1 more. So when you do that, you discover that we get 3 times A dagger N plus 1. Or we get 3 A daggers and 3 A dagger N's. Notice that all of these terms change the vibrational quantum number up by 1. So there's a beauty to this algebra, because you know what you're going to get, and you have to do a little work to massage the terms to all come out, in this form. And you know you're going to have a term that changes the vibrational quantum number by 1, or from this you're going to have a term that decreases the vibrational quantum number by 1. And so these 3 terms are going to give you just 3AN. And so you should go through this, because you can fill sheets of paper doing the algebra, subtracting and adding terms. Or you can just say, oh yeah, I want to rearrange the order by doing a series of binary permutations. And once you've got the hang of that, then you just count the number of binary permutations and you multiply the orphan term, and you've got it. And so similarly for Q4, one has 1/4 times A dagger to the 4th, A to the 4th. And then we're going to have one term that has 1 more dagger than not, and 1 term that has, I'm sorry, we're going to have A dagger, A dagger, A dagger, A, 2 more daggers than not. And we're going to have 1 term that's A dagger, and we'll have other terms that have this combination. So these are going to change the vibrational quantum number by 2, increase it by 2. These are going to decrease it by 2, and these are not going to change it. We already know from what, however you saw matrix elements of Q in your previous life, you know that there's going to be delta V of 4, delta V of 2, delta V of 0, delta V of -2, delta V of -4. And it's nice to be able to get them without having to do an awful lot of work. Now you could also have a computer set up the matrix for Q and then do matrix multiplication of those things. And that's easy to instruct a computer to do too. But this is nice because you actually arrange things and you discover how to put things together without doing a lot of work. Okay, so with this algebra, you're really in a position now to write down all of the necessary perturbation theory to solve the problem. And in addition, you've got a handout with this lecture which actually does it. So there's not too much trouble actually doing this problem, but I think you really want to go through the paces using this stuff. Okay, so now I don't think many of you are interested in making a career doing spectroscopy on diatomic molecules. But one of the nice things about diatomic molecules is everything we can almost everything we can do for diatomic molecules, we can do for polyatomic molecules. And the things we can't do for polyatomic molecules, like get a potential energy curve by the rydberg-klein-rees method, which you can do for diatomics, well, you can't do that for polyatomics. So you have to take something from diatomics and extend it. So suppose we have this triatomic molecule, a bent triatomic molecule. And we know that it belongs to the C2V point group. The point group has 4 irreducible representations. And it's a triatomic. You don't really need fancy techniques. There's going to be a symmetric stretch, there's going to be a bend, and there's going to be an antisymmetric stretch. So we have the symmetric stretch, that's nu1, and that'll be A1. And we have the bend, and that'll be called nu2. And then we have, and that's A1 also. And then we have the antisymmetric stretch, and that's B1. That's nu3. Okay, so if you don't know group theory, you will learn it. But the important thing is this is called the totally symmetric representation. The Hamiltonian is totally symmetric. If a Hamiltonian is a product of 3 things: wave function, operator, wave function. The operator in the Hamiltonian has to belong to, let me back up. The Hamiltonian itself belongs to the totally symmetric representation. One can have off-diagonal matrix elements of the Hamiltonian, but those are terms in the Hamiltonian which combine with other terms in the Hamiltonian to leave the thing being totally symmetric. So the thing that I got wrong in writing lecture notes 2 and 3 previously was I said we're going to have a linear molecule and we have the x bend and the y bend. And the problem is the way I formulated the problem, the matrix elements, or the terms that I used in the Hamiltonian, were not totally symmetric. They didn't respect cylindrical symmetry. And so that was all completely crazy. So now I'm careful to choose a bent molecule. We'll come back to linear molecules eventually. But the important thing is that the Hamiltonian, if you write down something, that thing is going to connect basis functions that belong to the same irreducible representation. Okay. So what we want to do is take what we learned from allowing a diatomic rotating molecule and vibrating molecule to be anharmonic, to extend that to the vibrational levels of a triatomic. And so we're going to have diagonal anharmonicity in each of these modes, just like what we did for a diatomic. But we're also going to allow these modes to couple to each other, involving terms like Q1, Q2, say Q2 squared, or Q1 squared, Q3 squared. Okay, A1, A1, B1. So we can have any powers of modes 1 and 2. But if we have mode 3, we have to have even powers of mode 3 for the legal coupling terms involving mode 3. So we're going to want to deal with the vibrational energy levels of a molecule with both diagonal and off-diagonal anharmonicity. And we'd like to relate the things that we measure in the spectrum from differences between energy levels to things that are constants in the potential, like K1, 2, 2, because one of these, two of these, K122, or this K1133. So these are the new things that we want to bring into explaining the molecular energy levels. Are we all okay? I haven't had any questions. I have seen some responses. And so I think most of you are at least semi-okay here. Are we all right? Okay. So I want to illustrate the use of perturbation theory and the use of judgment. So what I'm going to do is say, okay, omega 1 happens to be almost exactly 2 omega 2. And omega 3 is approximately 1.2 omega 1. So this is telling you that omega 1 and omega 2 are resonant. That we're going to get, when we do perturbation theory, we're going to get an energy denominator that's near 0 for certain terms coupling normal mode 1 with normal mode 2. But normal mode 3 is not going to have surprising denominators with either mode 1 or mode 2. So that means that the coupling between modes 3 and 2 and 3 and 1 can be handled by ordinary non-degenerate perturbation theory. But the coupling between modes 1 and 2, we have to be careful. So let us write the perturbation term. And the perturbation term contains terms like this: K122, Q1, Q2 squared. This just tells you what exponents to write up here. And as soon as you know what exponents to write up here, you know the matrix elements. Okay, and then there's another term, 1/4, K1133, Q1 squared, Q3 squared. And then let's write a third term, 1/12, K2233, Q2 cubed, Q3 squared. So here's a cubic term, a quartic term, and a quintic term. Why did we stop? Why not write more? There's no reason why we have to stop with quintic terms, and there are perhaps cubic and quartic terms that I haven't included here. Why didn't I write them? Well, we want the simplest possible representation. Mode 3 is not totally symmetric. So anytime we're coupling to mode 3, we have to have two of them. So we could conceivably have Q1, Q3 squared. We could have Q2, Q3 squared. But what you see here is that the frequencies for modes 1 and 3 are nearly the same, but they're not resonant. And so if you change V1 down and V3 up, you're not going to be near resonant. You're not going to have trouble. So you don't really need these terms. This one, though, because mode 1 is roughly twice the frequency of mode 2, this is a resonant term. This is very important. There's this one where we have modes 1 and 3 to the same power, and they're similar in frequency. They're not resonant, but it's the lowest ordered near resonant term, and you're going to have some relatively small energy denominators which will make this one important. This is quintic. Okay.
But doesn't that resonance depend on how big, say, omega 1 is? Because,
Yes.
you know, if your energy difference is large, then that resonance may not necessarily be
Right.
larger than the other ones. For sure.
That's right. Okay, so, but what I wanted to point out is that the quintic terms, I mean, the cubic terms make generally a factor of 10 larger contribution to the energy than the quartic terms, and these a factor of 10 larger than the quintic terms. There's more stuff that actually, so part of that came from that scaling, which I think we've lost by now, the factors that I pulled out of Q. And so, because each of those factors had 1 over the square root of omega in it. And so each time you have another Q, you get another factor, 1 over square root of omega. Omega is usually 1,000. So the square root of that is 30. And so just that factor kills you by a factor of 30 per Q. And there are other factors. So you get roughly a factor of 10 per power of the coordinate. And that means you generally want to look very carefully at the cubic ones. You look very careful at the quartic ones, because the quartic ones, remember in perturbation theory, we have energy, which is, for the ith level, is EI0 plus EI1 plus EI2. And this guy comes from just I1. It comes from a diagonal matrix element of the perturbation term, no energy denominator. And so if there is a quartic term, if there is a term that can have a diagonal element of one of the perturbation terms, that's going to be important. And so we look for things where we have 1133 or 1122, because as Q squared has matrix element delta V of 0 and plus and minus 2. And so you can get 2 delta V's of 0, and that's the same thing as saying, okay, this is, you're going to have some diagonal matrix elements of the perturbation operator. And they become really important. Yes?
Why is the third term important?
It isn't.
Okay. I don't even see how it's near resonant.
It isn't. It's just, I just wanted to include a quintic term because we want to kill it. Okay? All right. So, that's all. I just had to have an example. And there's another thing that happens. When you just look at the magnitudes of these terms, they decrease by roughly a factor of 10 per power. But the even powers appear in first order, and the odd powers appear only in second order. And so it turns out that quintic in second order, cubic in second order is roughly the same order of magnitude as quartic in first order. And quintic is just out of business, because there's no quintic in first order, there's quintic only in second order. That makes it roughly the same magnitude as sextic in zeroth order, in first order. And so, this is why we stop here. We don't generally want to look at quintic terms, because they're really small and they only appear squared over an energy difference. Okay. So, we're going to want to get from perturbation theory the expressions in this general energy expression. I just use a bold V to indicate all the vibrational modes instead of having to write E, V1, V2, V3. But that's what this means. And so we're going to have omega I VI plus a half plus I J I greater than or equal to J X ij vi plus a half v j, I can't write this, vj plus a half. And so we're going to have 3 omegas. We're going to have 6 x's. And we're going to want to get the 3 omegas and the 6 x's out of the expression for h prime. We have these, this, we don't have that, and we have the mass factors and the force constants. So we're going to use perturbation theory to get all that information. Okay. Now, it doesn't really matter if I don't finish these notes. I won't, because I've already done the important stuff. You know, the important thing is that we're going to use perturbation theory. We have a trick for simplifying all of the matrix elements. We have a way of telling a computer how to evaluate all the matrix elements and how to assemble them. Okay, but there's some more really beautiful stuff here that I want to talk about a little bit. Okay, so you know the formula for the first order correction to the energy. That's the diagonal element of the perturbation term. You know the formula for second order corrections. We have E2i is going to be the sum over j not equal to I, h I j h j I over E I 0 minus E j 0. These things are just combinations of omegas. So the energy denominators are really easy to write because it basically, you know, you have energy levels which are expressed as, you know, 3 quant of mode 1 plus 2 of mode 2, et cetera. And you take those differences, and there's just some number times the different values of omega. So this is easy. These are easy too because they're matrix elements of things like Q1, Q2 squared. So you can write these things down, and generally they're matrix elements squared. So you get square roots of things from this, and you just kill the square roots. Okay, and so there's all sorts of very wonderful things. But now, again, suppose you had Q1, Q2 squared. You want to make a list of all of the possible non-zero matrix elements. So we have delta V1 plus or minus 1. We have delta V2 of 0 plus or minus 2. And so there are if we write delta V1, delta V2, for the possible selection rules, we have plus 1, plus 2, minus 1, plus 2, plus 1, minus 2, minus 1, minus 2. So there are 4 possible combinations of off-diagonal matrix. Now, as soon as you write this, you know, oh, well, my goodness, A1 dagger, A2 dagger squared. The term that you want that controls this guy is that. The term that you want for this is A1, A2 dagger squared. So all of the possible non-zero matrix elements tell you, go and get this combination of A's and A daggers, and what was the number in front of that you got when you expanded Q? And this is very easy to tell a computer what to do. And so you write down an operator that expresses the anharmonicity. You break it up into selection rules. The selection rules tells you which combination of A's and A daggers. And then the little algebra you did at the beginning on the Q to the whatever enables you to finish the job. The rest is awful because you're manipulating these huge sums of things which involve matrix elements of lots of constants in the numerator. And in the denominator, you have differences in omega 1s and omega 2s, or sums of omega 1s and omega 2s. But it's all automatic, and you can work that out. OK. So you're proceeding along, and you're systematically writing down all the terms in the perturbation expansion, the second order perturbation expansion, and all of a sudden you get some number over 0. And you know that this is bad. And that corresponds to a resonance. You know, as soon as I wrote omega 1 is approximately equal to omega 2, omega 2, we're going to have a resonance whenever we have delta V1 is equal to minus 2 delta V2. And so we can do this two different ways. So there are going to be two different resonance terms. And as long as we stay away from those resonance terms, second order perturbation theory is fine. But we have to do something that respects these resonant terms. So what do? We have non-degenerate perturbation theory. That means not degenerate. Well, if you have degeneracy, you have to say, oh, forget order sorting. I have to solve a secular equation. I have to write down a block of the Hamiltonian, which I find the eigenvalues and eigenvectors of. And that deals with the resonance. And so it just tells you, OK. And so suppose we have what we call a polyad quantum number. This is just a way of saying, oh, well, what's resonance? And that is 2v1 plus v2. OK, and so this is a little code that says, suppose I have the 10th, p equals 10. I can then write down for p equals 10 all of the zero order states that are resonant. Let's just do it. I don't have p equals 10 in the notes. So I know that to get p equals 10, I can do that with 0, 10, right? I can get that with 1, 8. I can 2, 6, 3, 4, 2, 4, 2, and 5, 0. 1, 2, 3, 4, 5, 6. So there's 6 zero order states in this polyad with p equals 10. So that's a scaling rule for membership. That's a rule that says, OK, I've recognized what is the resonance condition that combining things this way. And so since omega 1 is twice as big as omega 2, for each quantum in omega 1, I get 2 points. For each quantum in omega 1, I get 1 point. That's where these polyad numbers come from. And then as soon as I say what this is, I discover that I have a 6 by 6 or whatever matrix that I have to diagonalize. And then I recognize that I only have couplings between successive members in this list. And so I can write the matrix, and it's going to have the form of, in this particular one, zeros, numbers, zeros. And so then the job is just to fill out these numbers. And the nice thing about this is all the trash comes out in front. And these are just square roots of integers. And so all of a sudden you get an effective Hamiltonian with trash, which you can or cannot, if you choose to, deal with. And then the critical structure, which is universal, along the diagonal. And depending on which value of p, you get a different matrix. But it's got the same structure. And there's only one thing that controls the energy levels, and that's this trash out here. And so what you've done is you've dealt with a resonance. That's a classical resonance because you got two things that oscillate at integer multiples. It's a quantum mechanical resonance, and you just wrote down some problem that you have to solve to get the correct linear combination of states that deal with that resonance. Now, the next thing you have to do is to say, well, hold your horses. We could do this, but there are, and this is the last thing I'm going to say, so you don't have to get impatient. I'm not going to cheat this. Again, we're done. But so the Hamiltonian is arranged in the form of blocks along the diagonal, and as you go down, the blocks get bigger and bigger. Each of these blocks is generated by the same constants in the previous one, and so there's nothing new except that you have to write them down. But sometimes there are matrix elements outside of blocks, and you have to fold them into the blocks before you diagonalize them. That's called a Van Vleck transformation. It's a fancy kind of second-order perturbation theory. And so what you do is you say, okay, if there is an out-of-block state that interacts strongly between these, that has a strong enough interaction between these two, that could mess up the detailed structure in here. We fold the effect of this state in here. And so what do? You say the transformed Hamiltonian correcting for out-of-block states. So here we have the ij element in a block. We write that as I, k, k, j, and these are perturbation terms, sum over k, and we have e I 0 plus e j 0 over 2 minus e k 0. Now this is a formula that was proposed by Van Vleck, and it looks just like second-order perturbation theory. We have a product of off-diagonal matrix elements, but it's a product where the initial and final index is different. And this is an average over the initial and final zero-order states within the block. And that's not a big deal because the energy difference within a block is small compared to the difference between states in the block and outside the block. And so basically, this is just a computational simplification. And so we have energy differences, we have matrix elements, and that provides us with a way of compensating for the effect of out-of-block, not resonant terms on the intra-block energies, and that improves the accuracy of the calculation. And that's really the whole story. And so I don't want to say any more. This algebraically is awful, but again, once you've taught your computer the other stuff, you can teach the computer this too. Because there's nothing new here. And there's nothing new here. Again, it's just integers times trash. And so that's it. This is an example of, you start with the effective Hamiltonian for a one-dimensional system, and you deal with anharmonicity. And you discover that you simplify the coupling terms into a form that's really, really convenient for sticking it to Mr. Computer. And then you say, okay, well, now we have several oscillators, and we have the diagonal anharmonicities. We know about that. And we have the cross anharmonicities between the different modes. And we just represent them phenomenologically as coupling terms. And we have a sense for which are the important ones. And then we say, be careful of resonance. And we have a way of fixing resonance. And then we're done. We have a machine that can represent the energy levels. It will not only represent the energy levels, it will give you things that are almost like wave functions with which you can calculate properties other than the energy, but you have to be careful. But you only have to be careful because of these out-of-block things. And that's a subtle thing, and most people can go through their life without worrying about that. But there is a subtle business here, and if you're a quantum chemist, you need to know about that because you're going to be comparing what you calculate against experiment, and it'll be apples and oranges. But for experimentalists, you don't really need to worry about that too much. So what we're going to start doing next lecture is start dealing with many electron atoms. And what I want to do is, I'm not going to teach you how to do quantum chemistry, but I'm going to teach you how you can see the periodic structure, the periodic table, in the control parameters that you use to build the energy levels of atoms out of. And that then provides us with a machinery that enables us to understand something about the energy levels of molecules. And so when I started teaching this at MIT, actually, I felt I have to show how the periodic table enters into the spectra of things. And it's really a tremendous battle. It's not so hard for atoms, but it's really hard for molecules because you lose the spherical symmetry. But there's still ways to make contact with periodicity. And this is one of our central concepts, shell structure, and certain orbitals are small and shield well, and other orbitals are big and don't shield. And all these concepts, we learn as freshmen. And it's certainly why I became a chemist. And so as a spectroscopist, I want to do more than lip service to that. And so we're going to go through some fairly elementary stuff on many electron atoms and then get into molecules. And I think then it'll be a more traditional trajectory through the relevant spectroscopic theory. And but I do love atoms, and you'll probably say enough atoms already. Okay, see you Wednesday.
Well,
Yeah.
you mentioned that the kind of resonance that you showed there, where omega-1 is approximately is an analog to a classical resonance, because they're
Yes.
oscillators that are oscillating near multiple of each other.
Yes.
So 2 questions. First of all, how close do they have to be before you start caring?
Well,
And is there some other kind of resonance that also comes up that's somehow inherently quantum mechanical and there's no, or what did you mean when you called it a classical?
well, you've been in your car, and its wheels aren't quite aligned, and you're going over some road that has periodic structure, and at a certain velocity, you discover you'd better slow down or speed up. And that's a resonance, because there's a natural mechanical resonance in the car, and you're perturbing your system at an integer multiple or submultiple of that, and it starts absorbing energy. And resonance is what leads to energy moving from one part of the molecule to another. It's always resonance that controls most of the dynamics that we can understand. Now, when is it big enough? Well, the coupling terms grow as the quantum numbers go up. They go up as the square root, or the square root to the certain power of the quantum numbers. And the energy defect doesn't grow. And so a resonance will generally make itself felt eventually as you go up in energy. Conversely, if it happens, it won't go away. There is a special situation where you can tune into resonance very early, where at a very sharp angle of attack on the energy levels. And then you can detune from resonance because the levels move apart faster than the matrix elements can grow. But that's very hard to cook up. And so it's very typical that if there is a resonance, it just gets worser and worser. But once you've solved the problem of the resonance, it doesn't matter, because you're smarter than it, and all it does is scale. And so it scales in the number of resonant states and the strength of the resonance, but everything has been determined from the first appearance. What you need is the coupling term and the energy defect, and once you know those, it's all over. For the molecule.
So is the first type of resonance the type with a very steep angle of attack that only appears at a certain energy? You call that an accidental resonance?
Yes, I would call it accidental.
And the other type is a systematic resonance?
Yes, or global. And it turns out that you can have a very high order resonance, like you have 1 to 4 or something like that. Then The 1 doesn't scale, the 4 does scale, but they can crash through each other really fast. When it's a 2 to 2, it's really hard to cook up a problem that detunes from resonance, no matter what. And I found the algebra to do that, but I chose the wrong one in the paper. There is going to be a paper on effective Hamiltonians, which I will distribute to the class at some point, which is sort of my magnum opus, what I've been working on all my scientific career. And so there will be something that I will share with you, but that's neither here nor there right now. So thank you.